I will try to develop a 3-bit binary counter using flip-flops. So a counter that should count from 0, 0, 0, 0, 0, 0, 1, 0 to 7 like this. 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So this is how the counter should count, and then it will go back there. So going there, 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 there. Finally from here again, it's like a loop. Now remembering the flip-flops, if I remember the JK flip-flop truth table, this is Q, so 0, 0 gives a 0, 0, 1 gives 0, 1, 0, this one is not 0, this one is actually no change, sorry, 1, 0 gives 1, and then 1, 1 is toggle. That's how it was, the JK flip-flop. And when we tied the J and K together, we got the T flip-flop, which has the same input for both. So when T and Q, if you look at, when 0, it's no change, NC I can say, and when it's 1, it's toggle. So I will use this property, and I will use 3 T flip-flops to develop this counter, 3-bit boundary counter. So I will develop a synchronous one where all the flip-flops will have the same clocks. So I will need 3 flip-flops. Let's just draw them. And since I'm saying that they will be synchronous, the clocks will be the same. So it will be same clock. So that much we have clock. And of course I will use the T flip-flops. So let's say this is this significant. So this is Q0, which is Q0 is here, Q1 is here, Q2 is here. So this is Q0 there, this is Q1 there, and this is Q2. Now when I look at the first one, with each clock Q0, which is this one, the least significant one, with each clock the output changes. So essentially I want the input T here. This is sorry, this one should be again T here, and this is T here. So this T I want to be 1. I can just give 1 here, because with every clock, this one, the output changes, toggles, because we can see this is 0, 1, 0, 1, 0, 1. It's going like that all the time whenever the clock comes. So I want the counter to be as such. With each clock it will count the next number and go to the next binary number. So this is fine. Now when you look at the second one, which is Q1, this one, when the input T is 0, the output will not change. So we can see, if we look closely at this one, you can see that this is 0, 0 here. So after the second one, this is not changing. What was here, same here, what was here. But here it has changed, it has toggled, and it has toggled when this one is a 1. So I can just connect this Q0 to this input. If I do that, let's see what will happen. Here is Q0 is 0, so we'll use maybe another color now. So Q0 is 0 here, so this one is getting, this T is getting a 0, so this is not changing. But at the same time, when this has become 1, this T is now has an input as 1. Since this one has 1, with the next clock this one will toggle, because this is the input here now, and this is of course the next one. So for the input we have to look at the previous the present state, we can say. Similarly, if we look at this one, we can see that this one is not changing, not changing, not changing, not changing. It's only changing when both of them are 1. So all we have to do is we have to AND these two and then connect to here. AND means when both are 1, only then this T we'll get a 1. So until then, this to 1 0 0 0 0 1 1 0 1 1 1 0, this will not toggle. When this is 1 1, both are 1, Q0 and Q1 are 1. This T has 1 now in the current moment. So with the next clock it will toggle, so it will become 1 here. So this will become from 0 to 1, it will toggle. Similarly again, when 1 1 here, this will again toggle, and this 1 will again become 0 when it's counting back from 7 to again 0. So because it will count as a loop like that. So this is how we can make a synchronous counter. This is just a basic principle for making a synchronous counter using T flip-flop. So I just wanted to give this introduction.